Consider this riddle. A man travels 1,000 kilometers north, 1,000 kilometers east, 1,000 kilometers south, and ends up at the same location. How is this possible? If we look at this on a regular map, it would seem impossible. However, if we look at Earth as a sphere, it becomes evident that if the man starts off at the South Pole, then it makes sense. We're used to performing mathematics on a simple flat space, such as a map. But as we've seen, all maps have biases and can't accurately represent curved surfaces. Unluckily for us, our Earth, and even the universe our planet exists in, are all curved. Our goal in this video, then, is to reconcile these two ideas. How do we take a curved surface and create a map for it, such that it preserves the important features of the original surface, and that any biases can be patched up by applying some correction factor? If this is possible, instead of performing awkward math on the curved surface, we can perform the math on a flat surface, and then interpret the result on the curved surface through some correction factor. One obvious but naive way to make such a map for a globe is to take every point on the surface and project it to the equator. However, each point on this map actually corresponds to two places on the globe, making it impossible to interpret the result. One change might be to make two copies, one for the northern and one for the southern hemisphere. The only problem with this is if a person were to walk across the equator, we would need to instantly jump from one map to another, which is very awkward to describe mathematically. One map that would work is called the Stereographic Projection. Take any point on the surface and draw a line connecting this point to the North Pole. Then make a marking on where this line crosses the equatorial plane. This marking is where the original point gets mapped to. We can perform this procedure for all points except the North Pole, and we get a map that is infinitely big. However, notice that there is a unique relationship between each point on the map and each point on the globe. What's more important is that points that were close to each other on the globe remain close to each other on this map. This property will make performing math on this flat surface much less awkward. The only potential problem is that the North Pole is not included. To fix this, we can create a second map in a similar fashion, except using the South Pole instead of the North Pole as a guide. We also avoid the earlier problem of having two maps, since there is a large degree of overlap between these two maps. This overlap allows a smooth transition when working in one map to working in the other map. In a sense, we just proved that the sphere is a manifold, but let's be a bit more technical on what counts as a manifold. A surface is a manifold if it can be covered by open shapes. By open, we mean that each shape only contains the space inside it, and the outline of the shape doesn't count. As a result, these shapes must be intersecting. Second, each shape must have a nicely behaving map, which we've already spent time describing. For this example, a simple projection will do the trick. There's a few more details, but this is the high-level overview. One important thing to note is that manifolds don't need to be surfaces. They can be lower or higher dimensions, and our definition can even extend to abstract objects that are hard to visualize. However, it is easier intuitively to think of manifolds as surfaces, at least for now, but everything in this video can be carried over to other types of manifolds. We will now go through an example of how these maps can be helpful. Something mathematicians love doing is analyzing if certain functions are smooth or not. There are easy tricks to do so in regular space, but how might we do this if the function acts on a manifold, especially one we can't visualize? For example, suppose this function describes the height of the terrain of a planet. If we are curious if the terrain is smooth in a particular region, we look at the map for that region. Instead of the function acting on each point on the manifold, we move each point in flat space to the corresponding point on the manifold through our map, then apply our function. We now have a function that acts on flat space. If this function is smooth, then our original function will be smooth in the region our map covers. If we can do this everywhere on the original manifold, then the overall function will be smooth. This is a very common theme that we will repeatedly see. Looking at the entire manifold can be tricky, but we can look at things locally. Once we look at things in small neighborhoods, we can use our nicely behaving maps to move things to flat space. Then we can use the fact that our maps cover the entire manifold to make a statement globally. Next, we can talk about the tangent plane. On a regular surface, this is very easy to visualize. Simply draw a plane that contains vectors tangent to the surface at some point. But this definition doesn't make sense when talking about other manifolds. What exactly does tangent mean, and how would you describe a vector for an abstract manifold? For something more abstract, we can talk about curves instead, which basically map each point in time to a specific point on the manifold in a smooth manner. Then, given any arbitrary function on the manifold, such as this mountain range, we can determine how quickly the height changes in the direction of this curve at time t equals 0. Each curve then corresponds to a function that essentially takes in a mountain range and outputs how fast it's changing in a certain direction. This function is what we call the tangent vector. Visually, we see how this corresponds to the tangent vector we are used to. However, instead of being defined as a physical object, we've laid out the groundwork for it to be defined as a function, which can then be applied to abstract manifolds as well. A vector field is just an assignment of a tangent vector to every point in their manifold, such that they vary smoothly. By smooth, we mean that if we apply the same smooth function to every single tangent vector, the output will be a smooth function as well. For simplicity, we will focus our discussion on flat space, because it is easier to visualize and animate. The following is an example of a vector field. A solution curve is a curve that follows the tangent vectors at every point, such that they always lie in the same direction. The d over dx and d over dy components represent the magnitudes of the vector in the x and y directions. We see that the x component stays constant, while the y component steadily increases as we increase x. We can write this out explicitly by acting the x component vector field on the y component vector field to show that as we move in the x direction, the vector field in the y direction increases in magnitude. However, if we do the opposite, and by acting the y component on the x component, we see that the change is 0. If we take the difference between these two vector fields, we get something called the Lie bracket. Since these two terms are not the same, the Lie bracket is non-zero. One way to interpret this is if we travel in the x direction for a certain time, and then in the y direction for a certain time, the point we reach will be different than if we swap the motion, such as starting off in the y direction, then going in the x direction. And this is because if we first start off in the y direction, the y component of the vector field is still quite small, and we won't travel as far. The idea that the order in which we travel matters is surprising, since we're familiar with a regular Cartesian plane, where it doesn't matter the order in which we travel. This is true for all coordinate systems. So if we take the vector field to represent standard coordinates, and by that we mean points in the same direction, and has the same magnitude, then the Lie bracket will be 0. Another way to measure a vector field is with differential forms. Instead of asking how fast the vector field is changing in a certain direction, we can ask for the component of that vector field in a certain direction. For example, if we take the original vector field and measure it with the form dy, we end up with a function that takes on high values when the vector is close to parallel to dy, and low values when the vector is almost perpendicular to dy. dy here is known as a 1 form. We can also have forms of higher dimensions. For example, take two 1 forms together, and it's known as a 2 form. It will take in two tangent vectors and return a single number. We can visualize this by thinking about the two tangent vectors as an area, and when acted on it by our differential forms, it will return the projection of that area onto the area formed by our 2 form. Finally, a 0 form takes in no tangent vectors and returns a number. Another way to think about this is, well, 0 forms are just functions. Here is an example of a 0 form, and we will illustrate how we can turn 0 forms into 1 forms, then 1 forms into 2 forms, using a special operator called the exterior derivative. The exterior derivative is similar to the regular derivative in the sense that it essentially describes how fast an object is changing. In this example, applying the exterior derivative gives us 1 forms that point towards where the function is changing the fastest. Here is an example of a 1 form. We can compute the exterior derivative of this by breaking it up into components and asking ourselves, how fast does each component change if the other component was fixed? This result is not visually intuitive, but it is actually related to the curl. If we imagine these 1 forms as water flowing, then taking the exterior derivative at a point is equivalent to measuring the tendency for an object to rotate if it was placed at that point. This is known as the curl. Furthermore, if we take the exterior derivative of a 2 form, we will get a 3 form that is related to how fast water is moving away from a single point, known as the divergence. Viewers who studied vector calculus may have already recognized the directional derivative, the curl, and the divergence from these last 3 examples. But through the power of differential geometry, we are able to reconcile these 3 ideas as a single derivative. We can finally bring everything together to prove what is arguably the most important result in calculus, Stokes' theorem. But first, let us investigate how we can integrate on arbitrary manifolds. In regular space, integrating a differential form over some space can be seen as finding the area of some graph f by approximating the area first as rectangles, then making better and better refinements. The base of each rectangle is determined by our differential form, which here is dx. Suppose we wish to integrate on a circle, where the form we are integrating is given by polar coordinates, d theta and dr, which then combined give a very awkward shape to integrate over. And if our manifold had been more abstract, it wouldn't even make sense to ask for the area under some graph. Like always, we can map this to a flat Cartesian space using the function phi, which maps the angle to the x-axis and the radius to the y-axis. Note that in order to be a proper map, we need to exclude the line representing 360 degrees to ensure points that are close on the circle remain close on the rectangle. To do things properly, we need to introduce another map that covers this line, but that can be ignored for now. Instead of integrating dr wedge d theta over a circle, we can use this map to write everything in terms of x and y, and integrate over regular Cartesian space instead. However, it is not as simple as switching variable names. Note that the areas dx and dy defined on Cartesian space have all the same area, but the areas d theta and dr defined vary depending on the radius. Therefore, we need to add another factor, called the Jacobian, that will adjust for this difference in areas. Now we can talk about Stokes' theorem. Suppose we wish to integrate a 2 form that was a result of taking the exterior derivative of a 1 form. Recall that if we take the derivative of a 1 form, we get a differential form related to the curl. So we've drawn a curved arrow to help visualize that. If we integrate this 2 form over this region, it is equivalent to finding the total curl of that region. Continuing with this physical analogy, we can visualize the flow of water along the edges in each cell. The main idea is that in neighboring cells, water flows in opposite directions, canceling out the effect. What we are left with is flow around the boundary of the region. Therefore, instead of integrating a 2 form over an area, we can integrate a 1 form over a curve. This is Stokes' theorem, and it can generalize to arbitrary manifolds and arbitrary forms. Keep in mind that the above illustration only serves to give intuition for why this might possibly be true, by drawing inspiration from physics. In reality, we can't really represent a 2 form as 4 arrows. Just like the rest of this video, these mathematical objects can't actually be drawn visually. To gain a true appreciation of differential geometry, one needs to work through the rigorous mathematical analysis. But the animations and analogies presented here can hopefully act as a preview of and spark interest to what inspires this branch of mathematics.